All right, so to the left we have f of x plus c, where x plus c is inside. Very good. Okay, Reagan, what do we have for moving to the right c units? Good, good. So what's important to understand here is when we're inside the function, our shift is going to be left or right. And it's kind of backwards from what we want, right? The plus is moving us left. The minus is moving us right. It's a little backwards. It's going to happen when we're inside the function. Okay. On the flip side of things, Katie, how do we move up c units?
F of x and then outside of parentheses plus c.
Okay. Good. And then shifting down c units. Sophie, what do you have?
F of x minus c.
Okay. Anything outside of our function is going to affect it vertically. So outside the function, we're moving up and down. Inside the function, we're moving left and right. Okay? All right, what about some reflections? If we want to reflect the graph about the x-axis, okay, Devin, what do we need to do there? The x-axis reflection.
It would be f, and then in parentheses, negative x.
And then what did you have for 6, Devin?
Negative f of x.
What do we think? That's what you have? Eli, that's what you have? You have yours backwards?
I think, yeah.
Does anyone else have theirs backwards from what I have up here? Okay. Inside the graph is going to affect horizontally. Outside the graph is going to affect it vertically. So, Devin, if we have a reflection from here to here, is that affecting vertical values or horizontal values?
That would be horizontal.
Our horizontal ones are changing, or our vertical ones are changing?
Vertical.
Our vertical ones are changing. So let's go ahead and change this. Outside is going to affect our y values. Inside is going to affect our x values. Okay? So a reflection about the y-axis means our x values are changing. A reflection around the x-axis means our y values are changing. Okay? All right, vertical stretches and shrinks and horizontal stretches and shrinks. Okay, we've talked about over and over, outside affects vertical, inside affects horizontal, right? Okay, Mia, how do we vertically stretch or shrink a function? Okay, just for simplicity, I'm just going to have C, all right? Sometimes it's going to be a fraction, sometimes it's going to be an integer value, but that C is going to tell us whether it's a stretch or a shrink, okay? Up in number 1E, if we vertically stretched, did you have a number bigger than 1 or less than 1? Stretch.
Oh, big.
Okay. I saw a lot of 2x squareds for 1e. Okay, you vertically stretched it. So if c is greater than 1, we have a stretch. And if c is less than 1, we have a shrink. Okay. When we apply this, you're going to want to multiply your y values by c. Okay, so if you have a parabola and it's 2x squared, all of your y values from your parent function get doubled. Okay, if you have 3x squared, you take all of your y values and you multiply them by 3. Okay, all right, horizontal stretch and shrink. Are the rules exactly the same? What do we talk about up here? Inside, everything is opposite, it's backwards, right? So if we want a horizontal stretch or shrink, we're going to have that C multiplied inside. But when C is greater than 1, we have a shrink. When C is less than 1, we have a stretch. Okay, so our rules are backwards, and how we apply it is backwards. So since we have numbers bigger than 1, shrinking it, and numbers less than 1, stretching it, when we apply this, we're going to have to multiply our x values by the reciprocal of C. Okay? You have a 2 inside. That would be shrinking it, so we got to get our x's smaller. We have to multiply by 1/2. If you have a 1/2, let's see, a 1/3 inside of your function being multiplied, then you're going to have to multiply all of your x's by 3 to get the stretch. Okay? So we're going to do 2 examples and hopefully get them done in the 10 minutes before we have our interruption. Okay? So this is part of your notes. These are all the rules. What you write in your notebook are going to be examples. You can either do it on the back of the yellow piece of paper or in your notebook. I don't care how you organize. Okay? Okay. So your parent function chart is out. And what I'm going to tell you is the reason we are doing this is so that we can come up with a graph very quickly, okay? Throughout the rest of the year, I might ask you for like a domain or range of a parent function that's been transformed. If we can quickly think of our graph, we can move on to the rest of the problem, okay? So I know that we could make an XY chart and plug in values and get a graph. That's not what I want. I want us to be able to graph in a matter of seconds. Okay, so if we have our parent functions in our head, we can understand our transformations, our graphs come very quickly. Okay? All right, so I'm going to pull an audible here. I'm going to change that to a cube. Here is our function, x minus 1, the quantity cubed, minus 2. X minus 1, the quantity cubed, minus 2. And this is what your book is going to ask you to do. It's going to ask you for your parent function, okay? From our 8 basic functions, okay? What's our parent function? Nathan?
I want to say cubic function.
Okay, so our parent function is just x cubed. Okay? Any of the parent functions, I want you to think of the 3 main coordinates. Okay, don't draw this. I'm just drawing it for effect. We know that the cubic function goes through the origin, 1, 1, and negative 1, 1. Right? Those are the 3 coordinates I want you to think about. Okay? Well, what's happening here? We have x minus 1, the quantity cubed, minus 2. Okay? So think about it. Don't say it out loud yet, but think about it. What are our transformations? What is that minus 1 doing? What is that minus 2 doing? Reckon what is happening?
Minus 1 is right 1, and then negative 2 is down 2.
Shift right 1 and down 2. Okay. Excellent. So, with this parent function in mind, okay, we're thinking about it, right? It's in our mind. We are going to shift those 3 coordinates, right 1, down 2. Right 1, down 2. Right 1, down 2. And in a matter of seconds, we have our function. Okay, way easier than making an XY chart and trying to fill it out. Yes. So we're at the origin, right? Our graph goes to the origin. So we're going to shift it right 1, down 2. Our graph goes to the point 1, 1. So we shift it right 1, down 2. Our graph goes to the point negative 1, 1. So we shift it right 1, down 2. So those are our 3 points that are on the parent function. Shift it over and down, and then we can create the curve. Okay. Our domain.
All real numbers.
And this is so nice. What's our range? All real numbers. The cubic is the nicest to identify domain and range because it's all real numbers. It goes on forever in the x's, goes on forever in the y's. Now, probably the most unique part of this problem, it's going to ask you to write it in terms of f of x. Okay? We have defined f of x to be x cubed. So instead of writing x minus 1 cubed minus 2, we're going to write that inside of our function is x minus 1, and then outside is minus 2. If our function is already x cubed, then in function notation, we're just going to write that x minus 1 is inside the function, and minus 2 is outside the function. Okay? That way, we could apply this transformation to any function that we wanted to. Okay, this is like generalizing it. All right, we're going to do one more, and I'm just going to hope that they're a minute late on this, okay? We good? Okay. Okay, I do want to encourage you to do any of your stretches, shrinks, reflections before you shift it. Okay, shifting should be your last priority. Okay, in our last example, we only had shifts, so it didn't matter. But in this case, we have more than just a shift. We want to take care of it first. Okay, so first of all, our parent function is the square root of x. Okay, looks like this, right? I'm going to go ahead, 1, 0, 0, 1, 1, 4, 2. Okay. Our transformations, 2 things are happening. Okay. Well, what's happening with that plus 3? Madeline, what is the plus 3 doing? Okay, so we have the shift left 3. What about this 2? Ryan, what's that 2 doing? Vertical stretch. Vertical stretch of 2. Okay, so let's figure out the vertical stretch and then shift it to the right. Okay. So I'm going to go ahead, I'm going to do our parent function in green. Green seems to be like my lightest color. Okay. So this is our parent function. If we're going to apply the stretch, then all of our y values are going to get multiplied by 2. So this has a y value of 0. That's boring. This has a y value of 1. What's its new y value? Okay. This has a y value of 2. What's its new y value? Okay. So this would be the stretch of our function. Then we would need to shift it to the right. Okay. Left, excuse me, we need to shift it to the left. So these red coordinates are going to get shifted 1, 2, left 3. 1, 2, left 3. 1, 2, left 3. Okay. So then the blue function is what I would want. And whether you wrote this down or not, we can now erase it. And all I want to see is the blue. Okay. But we applied this stretch first and then did the shift. Okay. So you can either really lightly mark your points so you can keep track of your work, or you can think about them in your head. Okay. I do ask that I can clearly see 3 coordinates on your graph. In the case of in any case, if you just had a coordinate here and a shooting star, I can't tell, that's what I think it looks like. I can't tell if you've applied a stretch or not. If you just had a parabola with a vertex and then you drew a U, I can't tell if it's the same shape or it's shrunk or stretched. So I need a good 3 coordinates graph. That way I can see if it's its original shape or if it's stretched or shrunk at all. Does that make sense? Okay. So if you look at your parent function chart, like absolute value, a quadratic, a cubic, those square root, can you think of 3 easy points for those graphs? Okay. The origin, okay. Absolute value has 1, 1, and negative 1, 1. A quadratic has 1, 1, origin, negative 1, 1. Our cubic we went through, our square root we went through. We can always think of 3 easy points. We don't have to put too much thought into it. If we were to write this one in terms of f of x, then our function is going to have a 2 on the outside and an x plus 3 on the inside. So in function notation, I have the same thing. A 2 on the outside and x plus 3 on the inside. What do I need you to apply first? Stretches, shrinks, reflections, then a shift. Now, they haven't interrupted us yet, so I want to give you a hint about a homework problem. Okay? This is not a shift left 3. This is not a shift left 6. Why?
Because you can take a 2 out.
Because that 2 is affecting it. If there is anything in front of the x inside your function, it is affecting your shift. So this is actually a shift left 3 and then a horizontal shrink of 1/2. Okay? I think that there is a problem in your book where there is a coefficient for x, and so that will need to be factored out before you do your transformation. Okay? You are welcome to use your graphing calculator to check your work, but the whole point is to do this quickly without a calculator. Look at Friday. What does it say before quiz number 2? Function aerobics. Okay? We are going to become the functions, and I'm going to ask you to apply stretches, shrinks, shifts using your body. Okay? It's going to be our warm-up for our quiz. Okay? So you need to know this well enough to where when I put you up here in the middle of the floor and I give you a function, you can tell me what it looks like. Okay? All right. Well, my wish works because they haven't done it yet. They're not going to do it yet. So we just rushed all the way through that. Let's talk about this one. I know some of us have packed it away. That's fine. We'll just talk about this one together. Okay? Go ahead and brush it. Yes. Oh. Okay, perfect. I'll mark that down. All right, turn to your neighbor and tell them what the parent function is and what the transformation is.
Because if it was just a 3x, then it would be a horizontal shrink.
Okay, so we have the greatest integer function. I've been eavesdropping. All right, but that 1/3 in front of the x. The 1/3 in front of the x.
It's a horizontal stretch of 3 or 0.3.
3 or 0.3, which one?
3.
Good job. Okay, when it's inside, we have to think of the reciprocal when we apply it. So we're stretching horizontally by 3. So all of our x's are being multiplied by 3. So our parent function looks like this. Right? Oh, I don't need this many steps, but that's fine. Okay. So what's the x value of this open circle right here? Our x value is 1, right? Our y value is 0. Our x value is 1. So if our x's get multiplied by 3, what's the new x value? 3. Okay? This stair step has a closed circle at 1, so that's going to become 3. And an open circle at 2, so that becomes... Okay, so what's going to be true about our stairs? They're very long, aren't they? How, think about it, so fill it out. How would we make our stairs taller? If I wanted my stairs to be taller, okay, our coefficient would need to be on the outside instead of the inside. And Ryan, what kind of coefficient? We would need one greater than 1 so that we could stretch them vertically. Okay. This is about the only function to where a horizontal stretch does not act the same as a vertical shrink. All of your other functions, a horizontal stretch and vertical shrink, will have a similar effect on the graph. Okay. All right, so you are verifying your answers with a graphing calculator, but you're not using it to get your answer. How many coordinates do I want to clearly see? 3. Are you labeling them? No, that's a waste of time. I just need to be able to tell where they are so I can get the shape. Okay? All right. Perfect. Have a wonderful day.